Hi there, and welcome to this lesson on Further Pure Mathematics 2. And in this lesson, we're looking at what are called the nth roots of unity. But first of all, we'll take a few steps backwards. All quadratic equations of the form ax squared plus bx plus c equals 0, they all have exactly two solutions. So something like x squared equals 4 has got two real solutions, x equals plus or minus 2. Something like x squared equals minus 4 has still got two solutions, but both of them will be complex, x equals plus or minus 2i. And in the same way, all cubic equations have got exactly three solutions. And all nth degree equations have exactly n solutions. And they may well be a mixture of real solutions and complex solutions. The simplest polynomial equation is of the form x to the n equals 1. And it's solving this equation, which gives us what are called the nth roots of unity, or the nth roots of 1. The simplest case of this is where n equals 2, and we get x squared equals 1, which has two real solutions, x equals plus or minus 1. But although both of these are real numbers, they can still be drawn on an Argand diagram. And if you were to do so, you get something like this, with plus 1 on the positive real axis and minus 1 there on the negative real axis. Now, using that idea, have a go yourself and see if you can work out what the three roots are of z cubed equals 1. So the cube roots of unity. And then once you've found them, try and do a sketch of them on an Argand diagram. Pause the video, have a go yourself, and then come back when you're ready. Okay, let's have a look at how you do this. Z cubed equals 1. I'd rearrange that to get z cubed minus 1 equals 0. And the first solution you can just find by inspection. If z equals 1, then 1 cubed minus 1 is equal to 0. So z equals 1 must be a solution or a root of that equation. Now, if that's a root, that means that z minus 1 must be a factor of z cubed minus 1. Once you've found a factor, you can divide through by it to find other factors. So if we divide z cubed minus 1 by z minus 1, then we'll get this quadratic factor as well, z squared plus z plus 1. And we now need to find out when this quadratic is equal to 0. The way we do that is with the quadratic formula. And using the quadratic formula, we get that, which simplifies to minus 1, plus or minus the square root of minus 3 divided by 2. So that's three solutions. And the three solutions of z cubed equals 1 are, first of all, z equals 1. Then z equals minus a half plus root 3 over 2i. And z equals minus a half minus root 3 over 2i. We were asked to sketch those on an Argand diagram, and if we did so, we get something a bit like this. Plus 1 on the real axis, minus a half plus root 3 over 2i would be somewhere around here, and minus a half minus root 3 over 2i somewhere around there. Okay, following the same idea, let's go up one level and have a go at the fourth roots of unity. So do the same thing with z to the 4 equals 1. Pause the video, have a go yourself, and come back when you're ready. Okay, let's have a look at these. Z to the 4 equals 1, so I'll rearrange that again to get z to the 4 minus 1 equals 0. And the easiest way forwards from here is to notice that you've got the difference of two squares. So that will factorize into z squared minus 1 times z squared plus 1 equals 0. And then we can find the solutions from each bracket. So if z squared minus 1 is 0, that means z squared equals 1, which gives us z equals plus or minus 1. And if z squared plus 1 equals 0, that'll give us z squared equals minus 1, which gives us the two complex solutions, z equals plus or minus I. So those are the four solutions, plus or minus 1, plus or minus I. And if we were to draw those on an Argand diagram, that's what you get. Plus and minus 1 on the real axis, and plus I and minus I on the imaginary axis. Now, those two questions that we just did, in both cases, all the solutions would be on the circumference of a unit circle, a circle with radius 1, centered the origin. So I could draw a circle around those 3 points and a circle around those 4 points. And that turns out to always be the case. Each solution is a complex number with modulus 1. And that's true for any power of n. The solutions will always be equally spaced on the circumference of a circle, center 0, with radius 1. And the reason for that is otherwise the modulus of z to the n wouldn't be 1. Therefore, all the roots of z to the n equal 1 will have the form z equals cos theta plus I sine theta, because r will equal 1. So z will simplify to that. That's what we just said. And we're able to use de Moivre's theorem to find out what all the roots are. And with higher powers of n, it's a lot easier to use de Moivre's theorem than the method that we were using in the first two examples. And the way we do it is we say, well, z to the n equals 1. Z equals cos theta plus I sine theta. So that means that cos theta plus I sine theta to the power of n equals 1. Using de Moivre's theorem, we'll get cos n theta plus I sine n theta is equal to 1. Now, the solutions of this equation are those values of n such that sine n theta equals 0 and cos n theta equals 1. And the reason for that is this complex part here on the left-hand side has to equal 0 because there is no complex part on the right-hand side. So therefore, sine n theta must equal 0. And that just leaves us with cos n theta equals 1. So we're looking for solutions which work for both of these equations. Now, both of these equations do have exactly the same solutions, which are values of n theta, which are equal to multiples of 360 degrees, or multiples of 2 pi. And if n theta is a multiple of 360 degrees, then sine n theta will equal 0 and cos n theta will equal 1, where k is an integer. So for example, if we were finding the cube roots of unity, like we did in the first example, then we'd let n equal 3, so we'll have 3 theta equals 2k pi, which means that theta is equal to 2k pi divided by 3. When k equals 0, that'll give us theta equals 0. 2 times 0 divided by 3 is 0. And if theta is equal to 0, that'll give us the first solution of the cubic equation, which is cos 0 plus I sine 0, which simplifies to just z equals 1. And we always get z equals 1 when k equals 0. That is always the first solution when we're solving z to the n equals 1. To get the second solution, we let k equal 1. When k is 1, theta will equal 2 pi divided by 3, and z will equal cos 2 pi divided by 3 plus I sine 2 pi divided by 3. Now, in this instance, I will find these values on the calculator. Putting that into the calculator will give us z equals minus a half plus root 3 over 2i. The third solution will be when k equals 2. If k is 2, then theta is equal to 4 pi divided by 3, and z will equal cos 4 pi divided by 3 plus I sine 4 pi divided by 3. And again, if I put those in the calculator, I get z equals minus a half minus root 3 over 2i. And those three solutions are the same solutions that we got when we did the first example. So in general, the n roots of z to the n equal 1 can be found by generalizing what we did in the last example. And that gives us that z will equal cos 2k pi over n plus I sine 2k pi over n, where k goes from 0 up to n minus 1. And that will give us all n roots of z to the n equals 1. Okay, I'll let you have a go at using this yourself. So let's say we had the quintic equation, z to the 5 equals 1, and we had to find the fifth roots of unity and then draw them on an Argand diagram. Have a go yourself, pause the video, come back to me when you're ready. Okay, let's have a look at this. So when k is equal to 0, in this case, we'll get cos 0 plus I sine 0, which equals 1, which always happens when k is 0. When k equals 1, we'll get z equals cos 2 pi divided by 5, because n is equal to 5 in this example, plus I sine 2 pi over 5. When k equals 2, we'll get the same thing with 4 pi over 5. When k equals 3, same thing with 6 pi over 5. And the final solution, when k equals 4, we'll have 8 pi over 5. Now, for this question, I would not put these values in the calculator. In general, if you're just going to get some really ugly decimal for the answer, the normal thing is just to leave it in this form, where you have cos and sine of some multiple of pi. And if you were to draw them, that is what they would look like. So the first solution would be here, plus 1 on the real axis, as it always is. And then you go anti-clockwise, going round to the other 4 solutions. And these solutions are always equally spaced. So since there's 5 of them, the angle between each one would be 360 degrees divided by 5, or 2 pi radians divided by 5. So in general, that's what we said the n roots of z to the n are. Now, we could also find them in exponential form. And in exponential form, you get something extremely similar. The n roots would be z equals e to the power of 2k pi I divided by n, again where k goes from 0 up to n minus 1. Omega notation. It's something that we need to just consider at the end of this lesson. Now, z equals 1, as we've said, it is always one of the roots of z to the n equals 1. It's always the first root that you find. Now, the second root and the third root, they're usually denoted by the letter omega. And the second root is found when k equals 1. When k equals 1, we'll get omega equals e to the power of 2 pi I divided by n, using exponential notation. When k equals 2, we'll find the third root. And the third root will be e to the power of 4 pi I over n, again using exponential notation. But that is equal to e to the power of 2 pi I over n squared, where e to the power of 2 pi I over n is omega. So that is omega squared. So the first root is 1, the second root is omega. The third root will be omega squared. And the fourth root, in similar fashion, will be omega cubed. The fifth root will be omega to the power of 4, and so on, until we get to the last root, which will be the n minus 1th root, which will equal omega to the power of n minus 1. So omega notation. The n roots of unity are normally written down as 1, then omega squared, then omega cubed, leading all the way up to omega to the power of n minus 1, depending on whatever n is. If we add these roots together, so if you add all of the n roots of unity together, what you get is a geometric series. You get 1 plus omega squared, plus omega cubed, up to plus omega to the power of n minus 1. Now, it's a geometric series where the first term is 1, and the common ratio that we're multiplying by is omega. We can find the sum of that series using the formula for the sum of a geometric series. And if we substitute a equals 1 into here, and r equals omega into there, then we get the sum of all of the roots of unity is equal to that. Now, by definition, w to the power of n is equal to 1, which means this top bracket here is equal to 1 minus 1. That gives us 0, which means if we add all of the roots of unity together, we will always get 0 for the answer. That's an important result to remember. Okay, summary of everything that we've done so far. In general, the n roots of z to the n equals 1 are z equals cos 2k pi over n plus I sine 2k pi over n, where k goes from 0 to n minus 1. Or writing those in exponential form, z equals e to the power of 2k pi I divided by n, where k goes from 0 up to n minus 1. The n roots of unity are written as 1, and then omega for the first one, then omega squared for the second, omega cubed for the third, and so on, till we get to omega to the power of n minus 1. The roots of unity are always on the unit circle, which has center the origin on an Argand diagram. And the roots will also always be the n vertices of a regular polygon. And lastly, if we add all of the roots together, we will always get 0 for the answer. Okay, that gets us to the end of the lesson. If you've got the textbook, then turn to page 41, exercise 3E, and questions 4 and 5 are on the sort of thing that we've been doing in this lesson. Thank you very much for listening, and cheerio.